So this video is actually for section 9.5, but this semester we have skipped 9.4, so I wanted to go through 9.4 and give you some highlights of information that you're going to need to understand 9.5. So grab your textbook, turn to page 609, and remember, you can start and stop this video as often as you need to let this sink in, kind of look at it in your book or your ebook and think a bit on it, or go ahead and jump into 9.5 and it may make more sense looking at it that direction. I'm going to read a lot to you. Wish you all were here so that you could read most of this, if not all of this. So it does say, and again I'm on page 609 in section 9.4, you have highlighters, sticky notes, index cards, notebook paper, lots of stuff to soak in these pieces of information. In simple terms, a vector, derived from the Latin vecere, means to carry, and so it's a quantity that has both magnitude and direction. It's customary to represent a vector by using an arrow. The length represents the magnitude, and the arrowhead indicates the direction. Many quantities in physics and a lot of the courses you will study in the future can be represented by vectors. For example, the velocity of an aircraft can be represented by an arrow that points in the direction of movement. The length of the arrow represents the speed. If the aircraft speeds up, we lengthen the arrow. If the aircraft changes direction, we introduce an arrow in the new direction. There are things you can look at, but based on the representation you see here, it's not surprising that the vectors are directed line segments, or that somehow it's all related. So geometric vectors, if P and Q are two distinct points on an XY plane, there's exactly one line containing both P and Q. The points on that part of the line that joins P to Q, including P and Q, form what's called a line segment, or line segment PQ. Ordering the points so that they proceed from P to Q, and it's a directed line segment. From P to Q, or a geometric vector, it's denoted by a ray, PQ, and a directed segment. It's called an. We have an initial point, and we have a terminal point. So make sure you're jotting these things down, kind of thinking and pondering on these things. And I want to go to the top of the next page. At the top of the next page, I'm going to do a refocus. At the top of the next page, it says, note, in print, bold-faced letters, because you're about to see a lot of bold-faced letters, and those are our vectors. And you and I don't have a built-in feature where we just automatically write in bold, so somehow we have to denote what is a vector. So what is used to denote vectors in bold in our textbook, we have to do in our handwriting, we have to do an arrow placed over a letter to denote a vector. So I just did a few examples, because then we'll call this vector V, and vector W, and vector U. I need you to note on the top of page 611 that you and I can multiply vectors by numbers geometrically. When using vectors, real numbers are referred to as scalars. A real number and a scalar, it's just a number. Scalars are quantities that have only magnitude, no direction. Examples of scalar quantities from physics are like temperature, 32 degrees, speed, 47 miles per hour, time. We now define how to multiply a vector by a scalar. I'm going to skip over this piece and jump on down to see figure 48 for some illustrations, and you see some pictures. And it says, for example, if A is the acceleration of an object of mass m due to a force F, and some of this might be just like blah 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 to you, but keep reading it slowly, stop the video, then by Newton's second law of motion, vector F equals m times vector A. Here, m times vector A is the product of a scalar. The scalar is m and the vector is A. I do want you to note here is a scalar summary. And a lot of these you're going to be like, oh, yeah, I already knew that. Right, but I want you to realize it's no big deal, and yeah, you already knew that. 0 times a vector, well, guess what? It's 0. 1 times a vector, guess what? It's just the vector. -1 times the vector. Do y'all see that this is like no big deal? Hey, I've done this before. I know it. If you have an alpha and a beta, and they are added, and it's times a vector, we have this thing called distribution, and we can do that. The alpha times the vector v and the beta times the vector v, and you keep the plus in the middle. Oh wait, we could write the alpha out front and distribute it across the two vectors. Wow, this makes perfect sense. Or if you have multiplication, alpha times the beta times the vector, you can regroup and just do the alpha times the beta. You might want to pause and write some of those down or think on that, because now this is a different thing I want to show you. You and I are not going to work on graphing vectors as far as graphing them what you see right here. We will talk about it in 9.5, but you're not going to be tested on it like this. And so when you see this vector v minus a vector w, a vector v over here is going to be given to us. You see about its little angle and about its length. And if you were to go draw it over here in one of these other pictures, it needs to be the same direction, the same angle, the same length. It has to be, whatever this is, has to be identical here. And just to show you, when it says I want 2 of these, well, over here I would need 2 of these going that same direction, but twice as long. So I would need 2 this size, and that's what we've got, 2 this size. When you look here, the point I wanted to make on this is that there is a minus vector w. And when we do that, you see how this vector w, its size and its direction and which way it is going, if we want a negative, it's still going to keep this same line, but it's not going to go this direction. It's going to go the opposite direction. And in one of the videos in 9.5, you're going to see him reference that. And I wanted you to have a little bit of background on, whoa, what did he just do? That's what he was doing. Here, I want you to see at the top of page 612 a little bit more information about the magnitude of vectors. And you see this symbol. And I would jot down in my brain or in my notes that, wow, that looks like absolute value, but it's like a double absolute value, and we'll pronounce it as magnitude. I want to know the magnitude of vector v. That's all that little symbol means. It's like when you see this symbol here, when you see like the absolute value, and we'll go ahead and make it a -9, I know that there's a process tied with that symbol. That means I want the distance between that number and 0, and it's 9 spaces. These little vertical marks tell me a process. With these double vertical marks tell you a process. And so the process, well, let me finish. Since magnitude of vector v equals the length, right here, the length of a directed line segment, it follows that it has the following properties. I'm not going to go over the properties, but I am going to turn the page to page 614 and say, look, here's the process of what this means. The double bar, which we will say magnitude of vector v, oh wow, this looks familiar. I'm going to do the square root of some kind of a thing. I'm going to square it, and I'm going to add a b squared. Wow, this looks Pythagorean-ish. Ah, it does, because over here it says it's the length, and we're going to be dealing with triangles, and so it all goes together. But I just showed you something that had like a little a and a little b, and it's like, where did those come from? I'm at the bottom of page 613, and at the bottom of that page, I'd like you to highlight or point out just some of these pieces. You see I have a vector v, and I'm going to jump over all of this and go straight to the back end. And you can write a vector multiple ways, but I want us to focus on this one, where it has a scalar times the vector I part plus a scalar times the vector j part. This is a way that we are going to write vectors, but I need you to note there is a horizontal component and a vertical component, and it's almost like, well, duh. This a is going to be the horizontal component. The b is going to be the vertical component, not the I, not the j, the scalar in front of it. And so when you see right here, if we had a vector v, 5 times vector I plus 4 times vector j, 5, a positive 5 is the horizontal component, a positive 4 is the vertical component. Wait, horizontal and vertical, that sounds like a graph. Well, I'm glad you noticed, because we'll be able to put it on a graph, And we'll be able to go over, and I probably should have put some numbers here, over horizontally 5, and the plus 4 is vertically 4. I'll have a dot there, but more importantly, I'm able to draw my vector based on the horizontal, where'd they go? Horizontal and vertical components. I'm still in section 9.4, and I'm now on page 616. And on 616, I've got a note for you to put this on your formula sheet, your one-page, two-sided formula sheet. There's a whole lot of stuff going on here, and it's talking about force vectors and just a whole lot of stuff. I'm not going to take time to read it. You should. What I'm trying to get to is when it says there's a direction angle alpha. Notice, and I would jot down on my formula card that this direction angle is going to be between 0 and can include 0, but less than 360, and it does not include 360. That gets taken care of with the 0. What I want you to write down on your formula card is alpha is a direction angle. And here is a formula. A while ago I mentioned we can write our vector in multiple ways. On the other pages we had a couple of things, one I mentioned, one I didn't, where I said there is a horizontal and vertical components. And when you look right here, look at the things that get brought in for that same vector v. Our magnitude, that little formula we talked about for vector v, gets brought in. And oh, looky, cosine and sine. Cosine does relate to the horizontal component. See, it's in front of the eye. Sine does relate to the vertical component. See, he's over there by J. I want you to make a note of this. Put this on your formula card. I'm still going in 9.4. Again, you can start and stop this video as much as you want. You can just kind of listen to it and make some notes. Go ahead and start 9.5, but then probably refer back to the notes we've made in 9.4. On page 617, it says a model with vectors. I just want to mention a couple of other things for you to highlight and underline. And it talks about adding. If you want to take two forces, which are vectors, and add them because they're simultaneously acting on an object, then you get a vector sum, and it is called a resultant force. The resultant force produces the same effect on the object as that obtained when the two forces, F1 and F2, act on the object. I'd like you to highlight and underline that. We'll bring that back around. And the last thing I want you to highlight and underline in 9.4 is this right here, which I'm on page 618, and it says in this figure, and you see this figure, it is called a force diagram. An object is said to be in static equilibrium or equilibrium if the object is at rest and the sum of all the forces acting on the object is 0. That is what we just read about a while ago. The resultant force is 0. So I'm running on over to page 624. And on 624, I am looking at the dot product for 9.5. So, we've made it to 9.5. I went very quickly through 9.4. And before you actually start 9.5, I'd like you to go ahead and put a couple of formulas on your formula card. In other words, I would like for you to put one that it's called the dot product. I would like you to put dot product, which is this set of symbols, and this description on your formula card. You might want to go ahead and hit pause, and then you might want to unpause and put some more. Just a while ago we mentioned, gotta get it in the screen here. Just a while ago we mentioned, without all of this stuff around, magnitude of vector v. But notice what's going on here. The magnitude of vector v is getting squared, and then it says it's worth the same thing as a vector v times the same vector v. I would put that on my formula card. I would also go to page 625, and right here in the middle, I would jot down on my formula card, how am I going to calculate an angle between vectors? I'm going to slow way down in just a minute and give you step by step on what in the world we're talking about. But I just wanted to make an introductory video, do some background from 9.4, tell you what to go ahead and write down on your formula card, and then we'll back up and take off. I would jot down this formula on your formula card as the angle between the vectors. As you see here, the cosine of some angle, it's going to be vector u, not times, but a while ago we saw it's going to be called the dot product. So it's the dot product between vector u and vector v, divided by the magnitude of vector w times the magnitude of vector v. I want you to also jot on your formula card, there's this word called orthogonal. I would jot down orthogonal. How will I know if two vectors are orthogonal? They're orthogonal if the dot product of the two vectors is 0. That's it. Dot product's really simple. You do a quick calculation, and by golly, if it turns out 0, you get to declare this big old fancy word, orthogonal. I want you to write on your formula card these two pieces. When you're doing these two pieces, it's going to tie in to what's going to be called decomposing. But I want you to go ahead and get them on your formula card when we go to decompose. I think that's such a weird word. But when we go to decompose, you need these two pieces down here, because we're going to pull apart a vector into two other vectors, and one's going to be called v sub 1 and the other v sub 2. You need to write on your card that when I'm decomposing, I will do this to get my vector v sub 1. No biggie. All I got to do is dot product, magnitude, square it, times a vector, done. Right here, to get my second one, I'll take my original vector v, subtract what I get over here. Wait, couldn't do that sound again. There we go. I'm done a second time. So as I glance through, I think that's it. So it's now time for you to go back to your list and start working through one by one, very carefully, very meticulously, through the videos and the examples. It's just like we're in class. I talk a little bit, you talk a little bit, maybe you need to talk to yourself, you do some examples and we've got it, or you ask questions, and asking questions means you're either going to send me emails or you're going to back the video up and hear that piece again and be like, ah, I see it now. I am ending this video to say, hang in there, keep up the great work.